this video, we'll discuss proper transistor biasing, which is a necessary step in using a transistor as an amplifier. We'll also look at a very basic amplifier circuit, and we'll do some simulations. We'll also look at a simple switching network um, that can be used in some basic uh, switching applications. For a transistor to operate properly as an amplifier, it has to be set to its proper operating condition, or what we call a quiescent or Q point. This operating condition is accomplished through what we call biasing. Biasing is the setting up of transistor to its desired location in the active region in order to for amplification to function properly. There are a number of circuits that provide uh, proper bias to a transistor, and among them are the fixed bias circuit, the emitter stabilized bias circuit, and the voltage divider bias circuit. Here we have a common emitter amplifier circuit that use a fixed bias circuit to provide um, the correct bias to the transistor. So in this setup, we have the base connected to the positive terminal of the um, source through a resistance R sub B, while the collector terminal is also connected to the positive of the source through a resistance R sub C. When used as an amplifier, so the signal goes to the base. So this is the input here. Let's say here we have an input signal. So that signal goes to the base through a capacitor C1, and the output is taken from the collector through a capacitor C2. So the purpose of the capacitors is to block DC signals. So here we have an actual common emitter amplifier using a fixed bias. And let's do a simulation for this circuit. So here I have already prepared the circuit for simulation. So here's the circuit that I have prepared. So let's open it. So this is the same circuit that I showed earlier, and um, so this is the bias uh, of or the bias voltage, the source that provides the bias. So this is the transistor in common emitter configuration, and these are the capacitors. This is R sub B, and here is R sub C. So this is the input uh, signal, and we are to get the output here. So the output is measured by a voltmeter named V out, and also we are measuring the input to the amplifier. Now the input signal here has a peak value of 1 millivolt. Okay, so let's do a simulation right now. Okay, so the green uh, waveform represents the input, and as you can see, it looks almost flat because it is very a very low amplitude signal, or a very small signal. And the output here is the curve uh, colored blue. The we we can adjust the range of the voltage so that we can see the input signal clearly. So let's say we have here um, minus 10 millivolts being the minimum, and 10 millivolts that is the maximum. So as you can see, we can now see clearly the input voltage. It has a 1 millivolt maximum value. And as you can see, the output is very large that we cannot anymore see the maximum value of the output. So let's again go back to the original range. Okay, so there you are. So the maximum value of the output is, as you can see, it's around near 200 millivolts, while the input is just 1 millivolt. Okay, so there is an almost 200 uh, amplification that happened here for the AC signal. Okay, let us go to another application of transistor, which is transistor switching. So in amplifiers, the input voltages there, or the input signal, is in the form of an AC signal, so it is a varying signal. Now, if a transistor input is simply a DC source, um, we are actually using the transistor as a switch. So what do you mean by this? So let's say we have here a transistor, and let's say I have a voltage, for example. Okay, so let's see, this is 5 volts. Let's say I have a switch here. So if the switch is open, that means that there's no voltage applied to the input, and therefore V sub in is 0. So therefore, there's no current that flows through the base terminal. So I sub B here is equals to 0. If there's no base current for this configuration, which is a common emitter configuration, that will place the transistor into the cut-off region here. And therefore, I sub C there is almost 0, so I sub C is very low, almost 0. And that will actually pull the potential of this point, which is also V sub C, to, so there's no current here. Okay, so this is open. This point here is open. And therefore, V out here will be pulled up to V sub C. That means V out will become V sub C, or in this case, that would be 5 volts. However, let's say we close the switch. So that means that we are actually making V in equals 5 volts here. So there will be current actually, okay, and that current can actually be computed. Okay, so this is V sub BE. Okay, this is a BE, and this junction here is forward biased, so that means V sub BE here is approximately zero point 0.7, assuming this is a silicon transistor. So that will give us, if we perform a Kirchhoff's around this loop, okay, Kirchhoff's voltage law around that loop there, that will give us minus 5 plus 68 I sub B minus 0.7 equals 0. And we can actually compute for I sub B there. Um, so this is actually plus here because B sub B is this is a plus here, this is a minus. And that will give us around 63.2 microamps. So that means we'll be uh, using the curve that is somewhere here, okay, where this is 63.2 microamps. Okay, we can actually calculate the collector current using I sub C equals the amplification factor times I sub B, and that will give us 110 times 63.2 microamps. So I sub C there will be approximately around 6 or 7 milliamps. Okay, so it's that is the estimate for I sub C there. And once there's a current, so current flows through the base equals to this, placing the transistor in saturation region. So the transistor will be saturated and will operate here, okay, making this voltage between the collector and the emitter VCE, so this is the plus minus, approximately equals to 0. Okay, so that will pull this terminal here to ground, uh, so that the V out is approximately equals to 0. So in summary, if V in here is equals to 5 or 0, we have V out equals 5 volts. And if V in is equals to 5, we have V out equals 0 volts. So this is a classic example of uh, an inverter or what they call a NOT gate, okay, where the input is inverted. So if it is a 5 volts, it is 0 at the output. If the input is 0, the output is a 5 volts. So again, let's do a simulation for this transistor switching. So this is a similar circuit that we have a while ago for transistor switching, except that the beta is equals to 125. So let's go to our circuit. So this is our circuit. So here we have the voltage VCC used for biasing. This is our R sub C, R sub B, And I just put a resistor here just to make the input to the uh, base more accurate. So the output is taken from this terminal here, and we have a voltmeter there to measure the output, and this is the voltmeter for the input. So let's run it. Okay. So right now the input is zero as shown by the green voltmeter. So it's very small. It's 5 millivolts, so that is approximately zero, while the output is 5 volts. Okay, so we have a zero input, but a 5 volts output. We can also see that in this graph. So the blue line represents the output and the green line represents the input. So the input is zero, the output is 5 volts. So let me switch on S1. So as you can see, the blue line now becomes zero. Well, there's a small voltage, but it is very small. It's 76 millivolts. But the green line is now 5 volts. So this is the input, 5 volts, but the output is zero. If I open again, the input is a zero, represented by the green line, while the output is a 5 volts. Okay, so clearly this is an inverter circuit or in not